So in this video, we're going to review some properties of exponents and logs. To begin with, recall that an exponent, let's say we have a base of x and a power of x squared. And so the exponent in this case is the name of the power to which the x is raised to, in this case, an exponent of 2. And as we know, this is the same thing as x times x. The first thing that I want to look at is what happens when you multiply values with exponents. So suppose that I'm looking at x to the 5th multiplied by x cubed, for example. Well, given our definition above, we see that x to the 5th is just x times x times x times x times x. It's x multiplied by itself 5 times. So I'm just writing out longhand what x to the 5th is. And this is saying that I'm multiplying that by x to the 3rd, which is x multiplied by itself 3 times. And I see in total, this gives me x multiplied by itself 8 times, or x to the 8th. And that gives us our first rule, that when multiplying values with exponents, you add the exponents together, 5 plus 3, or 5 to the 8th. Why do we do that? We do that just because we're really just multiplying a sequence of x's 5 times and then 3 more times to get a total of 8 times. The next exponent rule that I want to talk about is, let's say that I have x squared and then I raise that to the 3rd power. Well, what does that mean? By our definition above, again, we see that, so maybe I should offset this as my second example. I'm taking this chunk x squared and multiplying by itself 3 times. So this is the same thing as x squared times x squared times x squared. Because I'm cubing it, I'm repeating this x squared 3 times. And this multiplied together, again, by our definition, this is just x times x times x times x times x times x. Or in total, how many x's do I have here? I have x multiplied by itself 6 times. So in summary, we see that x squared cubed, and generally it will always be the case that this is the same thing as x raised to the 2 times 3, because I have my x squared happening 3 times, and I end up with x to the 6th. Another important property of exponents is the idea of fractional exponents. So, for example, what does it mean if I'm raising x to the 1/2? Well, by considering some of the properties previously, we can see that x to the 1/2 times x to the 1/2 is going to be the addition of the exponents, or x to the 1/2 plus 1/2, which is equal to x to the 1, which is just x. So that means that x to the 1/2 is the power to which, when I multiply this by itself, I end up with an x again. Or in other words, it's just the square root of x. It's the number to which, when I multiply it to itself twice, I end up with an x again. And this generalizes. So for example, x to the 1/5 is exactly the 5th root of x. Namely, if I raise this to the 5th power, I will end up with an x again. And similarly, if I wanted to consider maybe x to the 3/5, using the exponent rules described previously, we could simply rewrite this as x to the 3 times 1/5. That's a weird way to write 3/5, but that's exactly 3/5 in the exponent, which by our property earlier, that's x to the 1/5 multiplied by itself 3 times. Or, in other words, we could think of this as x to the 5th, or x to the 1/5, or the 5th root of x cubed. So fractional exponents work the same way and use the same properties as non-fractional exponents. The final thing that I would like to talk about is negative exponents. So for example, if I have x raised to the -2 power, what does that mean? In order to understand this, I'm going to give an example of, let's say, x to the 5th divided by x to the 3rd. what's going on here? This is 5x's multiplied by themselves on top, and then 3x's multiplied by themselves on bottom. I see that I can cancel my x's, leaving just a 1 on bottom and an x squared on top, which is just x squared. Or, in other words, this is the same thing as x to the 5th minus x to the 5 minus 3, or x squared. What if I were to reverse this order? Consider, for example, if I had x to the 3rd over x to the 5th. We see that this will work out to be very similar. I have 3 x's on top, I have 5 x's multiplied by each other on bottom. I can again cancel out 3 of the x's, and I'm left with 1 over x squared. By our exponent rules, this is the same thing as x to the 3 minus 5, or x to the negative 2. And by definition, this is a notational definition to represent this expression. This is saying that 1 over x squared is the same thing as x to the negative 2, or namely that negative powers are the same thing as taking the multiplicative reciprocal of that value. So let's review everything that we just said with a set of exponent rules. Our first rule, that when I have 2x raised to a times x raised to b, that's going to give me x to the a plus b. When I divide and have x to the a divided by x to the b, I get x to the a minus b. When I have x raised to a and then that value raised to b, I multiply the exponents. And the fourth one that I just talked about was if I have x to the negative a, that's going to be the same thing as 1 over x to the a, the reciprocal of that value. Next, I'd like to talk about logarithms. So logarithms and exponents go hand in hand with one another. Let's say that I have an expression of x to the k is equal to some value b. What does a logarithm do? A logarithm is the inverse operation of exponents. So if I apply a log base x to both sides of this equation, it will undo the exponent, and I'm able to solve for whatever the exponent is. So this is saying that log base x of b is exactly equal to k. These two phrases are equivalent to one another. And what does this mean in practice? For example, let's say that I have the number 5, that's my example, and I want to know what power do I put on 5 to be able to get the number, let's say, 27. In and of itself, I want to isolate this variable and get the n by itself. How can I do that? I'm going to take the log base 5 of both sides, thinking of it as an operation that I apply to both sides of this equation. So I'm going to apply log base 5 to this side, and then I'm also going to apply log base 5 to this side, and the log base 5 of this is going to cancel, and I'm left with n is equal to the log base 5 of 27. And if I wanted to, I could plug this into my calculator using a log rule to be able to solve for what my n value is. Rather than go through a lot of details of the summary of this, I think it's important to know why would we want to do this. And we do this in order to be able to solve for where an exponent or a variable is in the exponent position. My summary of log rules, I haven't proved any of these rules. This should be a review of items from the past, that my log base b of m equals k if and only if b to the k equals m. This is with different notation, the rule that we just talked about. This is our definition of logs. And we see that the log base b of a product is equal to the log of the sum. log base b of m plus log base b of n, and this relates exactly analogously to the exponent rule that we saw previously. Similarly, for quotients, log base b of m over n is equal to log base b of m minus log base b of n. And finally, log base b of m raised to the n power is equal to n times log base b of m.